And next it's time for the quark family. So here's our up quark with relative charge plus 2/3 and our down quark with relative charge minus 1/3. Now you can see I've put them both as having about 1/3 for the relative mass. That's only very rough. The down quark is a bit more massive than the up quark. And then here's their corresponding antiparticles. Notice you've got the bar to mean antiparticle, and as usual, opposite charge, same mass, opposite charge, same mass. But you need a third quark, and that is the strange quark. So it is like a heavy down in the sense that it's got the same charge, but it's got a lot more mass. However, there is a property that a strange quark has that no other type of particle has. So, and the name they decided to give this property was strangeness. So a strange quark has, and even then they didn't realise which way around it was going to be. So a strange quark has -1 strangeness, an anti-strange has +1 strangeness, and all other particles have 0 strangeness. So if you look at this quark-antiquark pair, you can see same mass, opposite charge, but also opposite strangeness there. Okay, and now the thing about quarks is that they can stick together to make larger particles. And I'm sure you're familiar with these ones already. A proton, because it has 2 ups and a down, that's going to be plus 2/3 charge, plus another 2/3 charge, minus a third charge, and that of course is equal to your +1, that's the charge of the proton. And for the neutron you can do the same thing, you've got 1 plus 2/3 for the up, minus a third for the down, minus another third for the down, so overall that's no charge. And so this is how the quark model accounts for the charge of these particles, and you can also do the antiproton and the antineutron. And as you can see, these particles all have either 3 quarks or 3 antiquarks, and so we give them the name baryon or antibaryon. And this is only one type of particle that can be made from quarks. So another type, there are others as well, another type is called a meson, and the mesons have 1 quark and 1 antiquark, and so do the antimesons. So the mesons that you want to be familiar with are the ones that you can make just out of ups and downs, and those ones are called pions, and the symbol is a pi. And the charge of the pion is put in the top right there. So you can just distinguish between them. So if you look at the pi plus meson, we've got an up, so that's plus 2/3 charge, and then an anti-down, so that is a plus another third. So you can see that that's going to give a charge of +1 for that particle. The pi zero, there are 2 different pi zeros, and in each case you can see it's going to be 0 charge overall, and then the pi minus, we've got a D, and then an anti-up, so that's, get it right, minus 2/3, so -1 overall, and so that accounts for the charge of the minus pion. Okay, so these, the pions, all ups and downs. If you introduce a strangeness of +1, sorry, it's probably better just to say introducing a strange quark there, you get this group, and they're called the kaons. And a kaon, K+, is an up anti-strange. So again, we've got an up as plus 2/3, and an anti-strange is plus another third, giving +1 for the charge. But then this, because it's got an anti-strange quark in there, its strangeness is +1. So that's the K+. The K0, you can see again the charge is going to be 0, and so is the strangeness. And then the K-, we've got an S, so that's minus a third charge, and then an anti up, so minus 2/3, so that's minus 1 charge for this one. But we've got a strange quark now, not an anti-strange, so that means the strangeness of this particle is minus 1. And so you can see that this particle is the antiparticle of that one. We've got an anti-up instead of an up, a strange instead of an anti-strange, and then that gives us the opposite charge and the opposite strangeness. So these are the baryons you need to know about. These are the mesons you need to know about. And you need to know that anything at all made of quarks is called a hadron. Now that's important because what type of particles you're made of determines what forces act on you. And first thing tomorrow, we're going to be looking at the strong force, which does act on things made of quarks. But we're going to do a quick practice question now. So without worrying too much about what in strong interactions mean, if I tell you that the charge and the strangeness and the number of baryons has to be conserved, so the total before has to equal the total after, have a little go at this question. Okay, and the sigma baryons, they're not on the list of baryons we need to know, so they have to tell us the quark composition of that one. And now, what is this X? Well, charge conservation first. This has +1, this has 0, so we've got a total of +1 on this side. That's 0, so this one must be +1. So we get a total of +1 on this side. So its charge has got to be +1. And then if we look at strangeness next, we don't have any strangeness at all on this side. So total strangeness 0. And then over here, we've got a strange quark. So that is strangeness -1. So we're going to have strangeness +1 here. We're going to have an anti-strange. If we've got a strange, we're going to have an anti-strange there, so that the total strangeness on this side is also 0. And then lastly, baryon number. This is not a baryon, but this is. So baryon number on this side is 1. That is 3 quarks, so that's a baryon. So that's 1. So this one must be 0 baryon. So this is not a baryon, so it's a meson. So we've got one other quark to put in there. And we know we've got to make a charge of +1. Now the charge of an anti-strange is +1/3. So that means we want +2/3 for this one, which makes it an up. So it's the up anti-strange there.